Hi friends, welcome to GMK Tutorials. In this video, we are going to see about the current mirrors. Okay, current mirror circuits, right? So I think all of you having some basic idea what is meant by current mirror circuit. Okay, so how it is connected. Okay, that is some basic analysis. I think all of you having some basic idea, right? So let us see. So I think all of you having a familiar here. This is a circuit diagram for a transistor point of view. Here some current source. So there is some connection from this. So one more transistor here. So we can also call as it is generally called as a copy. Okay, copy of that current. Okay. So it is also connected to some VCC. So this current is generally called as a I reference. Okay. So this circuit is generally called as this circuit is generally called as current mirror circuit. Okay, this circuit generally called as a current mirror circuit. Current mirror circuit. So first of all, guys, can you think what is the use of this circuit? Why we are going to study about this circuit? Is there any necessity to study about these kind of the circuits? This is a very important question, right? So let us see. So there is some lot of data will be available here, like current mirrors. So what is the necessity of this one? Okay, why require such a kind of the circuits in our analysis? Okay, so basic biasing currents and all these are very required, right? So just I don't want to go through this one. This is all about some basic data related to this one. So what is the application of a current mirror circuit? So what is the use of this one? So these are all the different kinds of the related information. I don't want to much go through this one. Okay. So this is all about the different data related to the current mirror circuits. So my question is there any we can directly design the current mirror circuit? Is there any evaluation of this one? So that is a first question each and every one, right? So exactly. So there is some evaluation is there from previous circuits to in this circuit. So whatever the circuit we are seeing about here, so this circuit cannot directly taken in this form. So before this, lot of analysis is also there. So based on the analysis, this circuit is the best circuit for performing different kinds of the applications. Okay, so that is also very important. Basically, these current mirror circuits are very useful in case of the different purposes. Suppose if you can you think each and every day nowadays we are using most of the devices are maybe mobiles, laptops. Each and every devices are using with a constant supply voltage. If suppose if the supply voltages are varying, or maybe if the discharging of the corresponding devices takes place very rapidly, at that time obviously the amount of voltage can be drawn by the corresponding device is also increases. Therefore, obviously the supply voltage is also decreases with time. So this is also one of the serious issue. Suppose if you are not providing a constant current, obviously the performance of the device is also decreases. So for that purpose, it is a very important situation we need to provide. We need to develop a circuit. The circuit produces a very constant source or very constant current source to the device to achieve a very good performance in every situation. Okay, so that is a basic motto of current mirror circuit. Suppose if you are taking any mobile device, if you are taking any cell phone, the cell phone performance is very common for place to place. Suppose if you are taking a cell phone at a minus 20 degrees centigrade, at the same time if you go for minus 1 degrees or minus 20 degrees also, you will get the same kind of the performance of the mobile only. Otherwise, the mobile is also failure device. That means the performance of the device cannot be compromised in every aspect with related to supply voltage or maybe temperature variation. So for that purpose, we need to provide a constant current to the device. Obviously, the performance cannot be degraded by the supply voltage variations, temperature conditions. So that is the basic motto of current mirror circuit, to design a current mirror circuit to produce a very constant current source which will produce the current source without deviation due to the different parameters like in terms of a power rail variations or maybe temperature conditions. I think it is very clear, guys. Okay, so then we will move on to the so now we will move on to the situation here. So let us see. I think all of you having this is very familiar circuit parameters. So this is generally called a MOSFET, right? This is generally called a MOSFET. It is also having a gate terminal, gate, source terminal, drain. Okay, this resistance is generally called a biasing resistance. It is also called as a biasing resistance. This is generally called as a VGS, gate to source voltage. So this is a analog. This is generally called a like AC signal, right? So generally, if you take the gain of the MOSFET depends on the GM as well as the RD values. Okay, the gain of the MOSFET depends on the GM and RD. I think all of you having these familiar words in our basics, right? GM and RD, where RD is nothing but drain across the drain resistance. So here the problem is that if you want to increase the gain of the device, it is directly proportional to GM at the same time RD values, right? RD values. But the problem is that the GM value is not high, so that the gain is also very less. So if you want to achieve a more gain, obviously you need to increase the drain resistance. So that means obviously if you want to increase the gain value, at the same time you need to increase the drain RD value. That is very important. So for that purpose, we need to increase the RD value. So there is a problem with RD, that is nothing but if you are increasing the RD means that the maximum voltage drop is present across the RD element is right. That means maximum supply voltage is also dissipated across the corresponding RD element. So that is also not good for maximum cases. So for that purpose, instead of increasing the RD value, I can replace the corresponding RD element, some active element. So the here RD is nothing but a passive element. So I will replace the passive element by a active device or maybe another MOSFET. Okay, so that is the purpose here. So here replace RD with some active elements so that we can gain a high resistance. So obviously the gain of the circuit is also increases. That is the main thing here. So at the same time, at the same time, so let it be considered some analysis. It is nothing but M1. This is generally called as a MOS transistor M2. So here the thing is that instead of the RD, we are using some active element, basically like a transistor, field effect transistor or MOSFETs are generally called as active elements, right? So here the thing is that just if you are replacing the RD element with the M2 device, obviously we need to provide VGS. So this is nothing but VGS2. So this is nothing but VGS1, right? VGS1. So here the VGS1 is nothing but the corresponding biasing for the M1 device. VGS is nothing but biasing for second device, that is generally called as M2. Up to now it is very clear, right? So here the problem is that, so here the active element is generally called as a AV, that is nothing but this voltage output voltage. So here if you are taking a gain of the corresponding circuit at that time, obviously the gain of the circuit is depends on AV is depends on GM into RDS by 2. GM into RDS by 2. Why it is depends on RDS by 2 means the first circuit having a RDS, at the same time second circuit is also having a RDS. Suppose if you are taking a point at a output point of view, these two resistors are connected in a parallel configuration. Therefore, overall RDS is equal to RDS into RDS divided by RDS into RDS plus RDS. So that will give rise to RDS square by 2 RDS. These two get cancelled. You will get RDS by 2. That is the reason why we are replacing AV is equal to GM into RD. So here I don't want to consider about the signs minus GM plus VM plus GM, like not like that. Just my motto is nothing but what is the necessity of why we are replacing RD value. Okay, so just we will start our evaluation towards the current mirror circuit. Okay, that is the basic motto, right? So here the problem is nothing but, so whatever the active element we are using here, this active element is also having some biasing element, that is nothing but VGS. Okay, this is the active element is also having some biasing element. So what is that biasing element? So this biasing element is generally called as a VGS2. Obviously this VGS is also changes with variation. So there may be chances of supply voltage variation. If the supply voltage variations is also affects the current passing through the corresponding device also. That is a drawback actually. At the same time, this VGS is also changes with respect to temperature also. It may be changes with the VTH also. Like obviously this MOSFET is also depends upon the VGS. That is also one of the important. That is nothing but threshold voltage. Obviously, in turn, this threshold voltage is also depends on the temperatures. or maybe device parameters. So there is a we need more device. The circuit cannot be varying with the temperature and the perform and the variations in the process parameters. That is a very important consideration. We need to look about more a stable device that produces a constant current source without deviating from its actual value, right? So for that purpose, an active element is having a biasing. If you are replacing with the active element, the replaced by a active element. So that for that purpose, this is a very robust and practically more stable and variations to the supply. But the problem is nothing but the transistor with current mirror, we can get more current. Suppose these are the issues in terms of this one. If you are replacing the corresponding device with a current mirror, you can definitely get a maximum constant current. So just of all, we have to see what is the necessity. Just we will very little later we will discussing about the current mirror also. Okay. So that is a problem with that one, right? That is a problem with the corresponding circuit. So let us see here. There is some configurations we will take about in case of the bipolar transistor, which is also called as a BJT point of view. So BJT point of view, we will look about it. Okay. So this is nothing but a CE configuration. In CE configuration, obviously this is generally called the base terminal, emitter, and the collector. So it is generally called the CE configuration. So here also same thing. The load resistance is increases. Obviously the maximum voltage drop is also present. Here also same thing. The gain is also related in terms of GM into RC point of view. Okay. So that is a problem here. We need to maintain a constant device. At the same time, this RC value is also depends on, suppose this current, if you are taking this current is nothing but IC, this IC current is equal to beta times of IB. Or if you are closely observe this one, this collector current is also varying with the beta value. If the beta value changes, obviously the IC value is also changes. So if you want to increase the gain of the device, obviously we need to provide one more circuit to achieve the constant current source. Therefore, it leads the maximum gain can be achieved. So for that purpose, here I have to change the corresponding resistance value, RC value, with the active element. That passive element can be replaced with an active device here. So here the problem is that if you are replacing the corresponding passive element with an active element, obviously this active element is also biasing with RB2, right? So this biasing variations is also related to temperature variations or maybe power supply variations. So there is another scope is also there. Here also there may be changes in the collector current due to the temperature and supply voltage issues, because of obviously the bipolar junction BJT is also temperature sensitive device. So I think all of you having some basic idea. In case of the BJT, the minority charge carries are increases with the reverse bias due to the temperature. Every 10 degrees centigrade, it is also double, right? So there is some conclusions already there in our previous curriculum, or I think all of us studied that points also. The BJT is also very temperature sensitive in some applications point of view. So that is nothing but here also there is another issue for this one. Just for that purpose, there is another case. That means here also we need some constant current source device is also required. So that means we need to provide a biasing element. It is also called, I can call as another word, biasing element. Biasing element. So at the same time, if you go for here, so there is some situations. It is nothing but a common collector point of view. So in this case also there is a case will be there. This is a I biasing current and RL value. Okay, this biasing current is here this biasing current is produces, it is independent of RL value. So it does not depend on the RL value, it produces the output. So that's great actually. So it is not a problem. But the problem is that as per analysis, if you are maintaining the I bias value like this, suppose if you are increasing the load resistance RL value, at the same time gain AV is also increases. Is it possible always to increase the RL value? If you are increasing the RL value, the size of the device may be increases. That is also one more problem at all. In this case also, the same analysis for if you go for the MOSFET also same case. It is a source, gain, drain, gate, source, drain cases. Here also same thing. The I bias and current is also independent of the RL value. Okay, independent of the RL value. So up to now it is very clear, right? So that means up to now our conclusion is nothing but each and every case, in case of a transistor C configuration or maybe MOSFET configuration, common source configuration, there is some circuits are required for producing a very constant source, produces a constant current sources to achieve a maximum gain in the corresponding both circuits, like in case of a BJT point of view as well as in case of a MOSFET point of view. So because of the biasing elements also, there may be chances of variation in the corresponding device. So there is again I have one question mark is there. So if you are replacing each and every 4 cases, there may be chances of replacing one device or maybe one element or maybe one circuit to produce a constant current sources. Just I can call that circuit is generally called as a biasing circuit, biasing element or biasing circuit. So what are the characteristics of biasing element? This is very important, right? Suppose if you want to replace this circuit with some biasing circuit, biasing element. So what are the characteristics? What are the characteristics of biasing element? That is very important. That will be discussed in the next class. So thank you for watching GNK tutorials. Thank you.